Examples 5, 6, and 7 get quite a bit more involved. Okay, so the type here is we're looking at a salt. Now, when you look at a salt, now the strategy first is, okay, look at the ions, and are they going to change the pH in any way? So that's our first question. And then once we do that, we need to write an equation. Okay, our equilibrium equation. And for that, in this case here, we're going to have to find a Kb. So it turns out that, we were given a Ka for acetic acid back in example 3, and we're going to find out that if we take the Ka of an acid times the Kb of its conjugate base, when you multiply them together, they give you Kw. So we can figure out Kb just by taking Kw divided by Ka. So we got to work on that and make that make sense. And then once that, we can go through and do an ice box. And that'll let us figure out our various ions, and from there we can answer all our questions. So, first off, we have to look at this compound here. We have sodium plus, and we have acetate ion, and so we should recognize by now that sodium, comes from a strong base. It is not going to be interesting. It's not going to change the pH. It's going to be neutral. Put it in solution, doesn't do anything. But the acetate ion, that is the conjugate base of a weak acid. So if we're saying here's something that's a conjugate base, then we got to treat it as a base. So first thing is let's write out the equation for this, and that's going to be C2H3O2 minus. And like other bases, since this is a proton acceptor, we have to give a donor next to it, so we have water. And our equilibrium is that if that accepts a proton, it reforms the acid. And it's going to leave some hydroxides floating around in solution. And that's going to be the basis of our ice box. And with that ice box, we are going to end up finding the OH minus concentration. And that's going to give us the key to the various pHs and pOHs and things like that. Okay, we can see what happens here. This is liquid, so we're not going to worry about that value. Now, this little piece here, the fact that it reforms the acid, sometimes students think, okay, if it reforms an acid, that is going to make the solution acidic, and that's not true, because what it actually does is that it holds on to those protons, okay, so that there's a lot of hydroxides in solution. Well, not a lot, but there are some. And so that's going to make the solution basic. So reforming this acid actually helps the solution be basic, which is kind of interesting. Now, we need to have a K for this. Now, this is a base, so the K is going to be a Kb. Okay, so let's kind of deal with that little piece first. I'm going to go down here. And so if I talked about this equation, okay, the Kb, then you can see what's going to happen is going to be the concentration of C2H3O2 times the concentration of OH minus all over the concentration of C2H3O2 minus. Okay, and that's the value we really want. But if we go back and think about, well, the Ka, okay, if we're just talking about this acetic acid, well, we could see what would happen for acetic acid. I'm not going to write out the equation, but we know, yeah, yes, I will. Okay, so acetic acid, HC2H3O2, and what that's going to do is break up into H plus and C2H3O2 minus, or we could have put a water in there. But the Ka for that one is going to be the concentration of H plus times the concentration of acetate all over the concentration of C2H3O2, like that. And that one we happen to know is 1.8 times 10 to the negative 5, because that was given back in example 3. Okay, so we look at these two. If we were to multiply these two, the Ka times the Kb, you can see what happens is that here's acetate ion and here's acetate ion. They're going to cancel. And here's acetic acid and here's acetic acid. They're going to cancel. So what do we have left is we have H plus concentration times OH minus concentration. And we know what that is. That's the Kw. So Kw equals the H plus concentration times the OH minus concentration. And we already know that at 25 degrees, that's equal to 1 times 10 to the negative 14. So what we've found here is that if you take the Ka for a weak acid and you multiply it by the Kb for the weak conjugate base, for the conjugate base of that weak acid, and you multiply those two things, that they equal Kw. So the Ka times the Kb is Kw if this acid and base are conjugates of each other, and they are in this case. So what is that going to do for us? That means if I want to do a reaction up here using the conjugate base of the weak acid acetic acid, I can calculate its Kb, okay, by simply using this equation. So the Kb that I want for my equilibrium for my icebox is Kw divided by Ka, its conjugate acid, and I know that's 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, and that comes out to be 5.6 times 10 to the negative 10. Okay, so that is pretty small. Okay, that's going to be a very reactant-favored reaction, which is okay. I mean, we just know that, this guy here, is mostly staying over here as reactants. It's not breaking a lot of products, but it is enough to make the solution basic. We are making some OH minuses. So let's go back to our icebox now and kind of deal with this. So we have a 0.1 molar solution of acetate, and we're not putting in any acetic acid or hydroxide. We're just starting with the solution of this salt. And this salt, we saw this in class, we put that in solution and it made the solution basic. So this sodium acetate and water actually turned blue, and that's what we're showing, is that we're making some hydroxides here. And the rest of this is kind of standard. So minus x plus x plus x. So this is 0.100 minus x, and this is x, and this is x. So when I get done, my x is going to be my hydroxide concentration. Now, the K for this, okay, we said is 10 to the minus 10, so that's pretty darn small. So we can go ahead and do our assumption. So we're going to say assume that 0.100 minus x is pretty much the same as 0.100. Okay, I left off the first part. X is much smaller than 0.1, which it definitely is going to be. So I'm going to jump way down to the bottom of the screen and see if we can finish this equation. So I'm going to use x and 0.1, not 0.1 minus x, just 0.1, and put it into our K expression. Okay, a little bit messy. So here I say my Kb is equal to the concentration of, what was it again? Acetic acid and hydroxide. All over acetate, and I have to know now that that is equal to 5.6 times 10 to the negative 10. And notice again here, this was not given in the problem. What was given was the Ka. So you have to say, okay, knowing my Ka, I can find this Kb if I need it. So that's a useful little tidbit. Okay, we're saying from our icebox, this is equal to x, and the other part's equal to x, so it's x squared. And with our assumption, this is 0.100, okay, and that equals 5.6 times 10 to the negative 10, which is going to multiply that over as x squared is equal to 5.6 times 10 to the negative 11. Okay, and I don't want x, I don't want x squared, I want x, so I'm going to take the square root of both sides, and I need to go back and remind myself that that x is my OH minus concentration. So in some of the other problems, x comes out to be the H plus concentration, this time it's OH minus. So now I'll just go ahead and get my value here, which is 7.5 times 10 to the negative 6. Okay, because this is like 56 times 10 to the negative 12. Take the square root, so 7.5 seems like, about square root of 56, and 10 to the minus 6 is the square root of 10 to the minus 12. And so that's my OH minus concentration. And that's one thing we want to find. We need to find our other ions, okay, or other species. So our acetic acid concentration, okay, is also X, so that's also 7.5 times 10 to the minus 6. And what about our acetate? Our acetate concentration, okay, is 0.1 minus 7.5 times 10 to the negative 6. Well, that's, nothing. That's 0.00000075. So that is definitely about 0.1. So we can see our assumption there was very good, that the value, that saying that 0.1 minus this value here is the same as 0.1 is very true. So here's our concentrations. Now, if I know my OH minus concentration, then the next step here is I can find my POH, and that's the negative log of my OH minus concentration, so 7.5 times 10 to the minus 6. And we can see, well, that value is going to be somewhere between 6 and 5, and in fact, that turns out to be 5.13. So that's my POH. And my pH, okay, 14 minus my POH, so that's 14 minus 5.13, and that equals 8.87. And that makes sense. My pH is greater than 7. And again, it's not hugely greater than 7. This is mildly basic, but that's, it's good. That's what it is. And that was enough so that our solution turned blue when we did this. Okay, and then last thing here is let's get our H plus concentration. So that's going to be 10 to the negative pH. Okay, 10 to the negative 8.87. And that comes out to be 1.3 times 10 to the negative 9. Oops. Negative 9 molar. Okay, so those are all the different values. Now, the last thing we want to do is say, well, what is our percent dissociation of this? Okay, so what we're saying, remember, percent dissociation, we want to take X divided by our initial value. Okay, and I'm just going to sneak it over here in the corner. I'll do it in yellow. Okay, and so our percent dissociation here is going to be X, which we said was 7.5 times 10 to the minus 6 divided by 0.1 times 100. Okay, and that comes out to be pretty small. Okay, and that 0.0075%. So very small dissociation, but that's okay. So those are all the values there for example number 5. Okay, example number 6. We can see the situation here is now we have a weak acid and we're also mixing a strong acid. So we have a weak acid and we're going to mix a strong acid with this. And not only that, we say, well, what's going on is we have C2H3O2 and we have HCl. Okay, so it turns out the Cl part of the HCl we don't care about. That's not going to do anything for us. What it is going to be the common ion effect. And so we're going to do an ice box. But in that ice box, we're going to have two different sources of H+. So we're going to be just kind of, we'll have an initial value of H+ in our solution. Now, the equilibrium we have to think about, well, the only interesting equilibrium here is the weak acid, acetic acid. So for that acid, then, we're going to write our equation. And we know that that's going to break up. I'm going to give us H pluses and acetate. And if we do an ice box for this, now I could have put water in, but I didn't. Okay, so I'm starting off, I have a value of 0.1 molar. And I have an initial value of HCl. So my 0.1 molar, this stuff here initially, I'm putting it in as acetic acid, but my HCl is going to give me some 0.1 molar H pluses as well, and 0 acetate. So kind of like common ions we've seen before, we have two initial values, and we can see what's going to happen. It's going to have to shift to the right, to reach equilibrium because there's 0 acetate. So it's going to be minus X plus X plus X. So at equilibrium we have X, we have 0.1 minus X, and we have 0.10 plus X. Okay, so the K for this one, okay, we know the K expression here is concentration of H plus times concentration of C2H3O2 minus all over HC2H3O2. And we have seen that again. We know that that is equal to 1.8 times 10 to the negative 5. That was given back in example 3. So of the different chemicals in here, the only one that we're really interested in as far as the K's and stuff is the weak acid acetic acid. And we can see what's going to happen here is, that is pretty reactant favored. So that means that X is not very big in the first place. And with this H, with a common ion, we know that's going to drive the reaction backwards. So it's going to make X even smaller. So the assumption we're going to make is that X is much smaller than 0.100. So therefore, 0.100 minus X is approximately 0.100. And 0.100 plus X as our final value of the H plus is also about 0.100. So the only X we're actually going to calculate is that one. So let's go ahead and do our icebox. And we can see what's going to happen is, if I go back to our Ka expression, I have the concentration of H plus times the concentration of C2H3O2 minus all over the concentration of C2H3O2, and we know that that equals 1.8 times 10 to the negative 5, and substituting our values in, this H plus is 0.100, and this is X, all over 0.100, so we can see what's going to happen. Those two are going to cancel out, so X is equal to 1.8 times 10 to the negative 5. So what is X in this case? X is our acetate ion concentration. Okay, and pretty much then, what are our other concentrations? Well, our H plus concentration, that's essentially 0.100. Okay, it's 0.100 minus 0.00, no, plus 0.000018, and that's not going to change it at all. So that's these concentrations. And our acetic acid concentration is going to be the same thing. It's also 0.100 molar. Okay, like we said. Now, what else can we do with this here? We have an H plus concentration. And with this we have, okay, hold on. Okay, I came a little problem here. Somewhere along the way I have gotten an old version of this handout, and this value here has changed. It is not 0.1 molar. Okay, it's half that much, so it's 0.050 moles, okay, which is going to change my calculations here. So this value here was not 0.1, this is 0.05. Okay, because it's in a 1 liter container, and so that's going to change this one. This would be 0.050 molar. Okay, so this assumption is still true. My this guy here is still essentially 0.1. Okay, my assumption here is going to change. So this is 0.05 plus X is essentially the same as 0.050 molar. Okay, so when I come down here, my, which one here? This H plus, this is 0.050 molar. So when I divide, they're not going to cancel out now, but it's still going to be simple. So This can be 0.05 over 0.1 equals 1.8 times 10 to the minus 5. Okay, so my X concentration, okay, these are all going to change. Well, this will be okay. And again, so this is going to be 0.050 molar. Sorry for all those mistakes. And you can see this is going to kind of double this number, so this will be 3.6 times 10 to the negative 5 molar. Okay, so I think I'm back on track here. So if I know my H plus concentration, okay, then I can go ahead and figure out my pH. So now my pH is the negative log of the H plus concentration. And so since that H plus concentration is essentially the acid that we added, the strong acid that we added, okay, it's going to be negative log of 0.0500 molar. And that comes out to be something as 5 times 10 to the minus 2, so it's between 1 and 2, and not surprisingly a pH of 1.30. Okay, so notice that this pH is essentially because of the strong acid that we added in. Okay, the pOH, okay, simply 14 minus the pH, so that's going to be about 12.70. Okay, and my H plus concentration, we already said, is 0.5. We can figure out the OH minus concentration. And again, we can say 1 times 10 to the minus 14 divided by 0.05, or we can say this is 10 to the negative pOH. Okay, either way, so we come up with 2.0 times 10 to the minus 13. And have we missed anything? We need to do our dissociation. So x over 0.1. So x in this case here was 3.6 times 10 to the minus 5. So our percent dissociation, 3.6 times 10 to the negative 5 over the initial value of 0.1 times 100. And that comes out to be 0.036% dissociated. So the idea is, that this acetic acid, usually breaks up a little bit more than 1%, but because of all this hydrogen that's in there already, because of the common ion, that drives the reaction backwards, so it's only going to break up much less than 1%, and that makes some sense. Okay, we're going to go on to example number 7. Okay, example number 7, here we have C2H3O2, okay, and we have sodium acetate. And again, somehow I've gotten the wrong values on here, so this number here is going to change to 0.050 moles. Okay, and that's not bad as long as we have that in the first place. So what is our reaction here? Is again, we have acetate and we have sodium acetate, we have acetic acid, but the actual stuff we want to deal with is this equilibrium, okay, the acetic acid. So I'm just going to write it here, C2H3O2 dissociates into H plus and C2H3O2 minus. And we have a value for that. We know that the Ka for that is, given back in example 3, it's the same Ka, 1.8 times 10 to the minus 5. But what's going on here is I have this value up here, and I've also got this value. I've got some acetate from my sodium acetate. Okay, so I have two initial values, and this is going to be 0. And then we're going to calculate everything from there. So the strategy we have here is that we have a weak acid, and we're putting in some of its conjugate base as well. Okay, so the strategy is we have common ions. Okay, the other strategy is we're still going to be using our Ka. Okay, so we're still, this equilibrium still has to do with just our normal acid equilibrium, because we don't have to write a new reaction here. And the sodium there, that's a spectator ion. We know that sodium does not change the pH, it's a neutral ion. And then we're going to just go back and solve our icebox. And when we do that, that'll give us an H plus concentration, and we can figure out the pH and pOH and everything. Okay, so let's just do it. So we're starting off here. We have a 0.1 moles of acetic acid in a 1 liter solution. So this is 0.1 molar. Okay, we have 0.05, so 0.050 molar. Okay, and we can see what's going to happen, pretty standard, that, because this is 0, it has to drive to the right. So this is going to be x, this is going to be plus x, plus x. So this is 0.100 minus x. This will be x at equilibrium, and this will be 0.050 plus x. Looks similar to the last problem. And also similar to the last problem is the idea that we can make our assumption. Okay, so assume that x is much smaller than 0.100 and much smaller than 0.05. So we really ought to say it's much smaller than 0.050. Okay, so therefore 0.100 minus x is just going to be essentially 0.100, and 0.050 plus x is essentially 0.050 molar. So I'm going to use those as my simplifying assumptions, and we're just going to go back and put this into our K expression. Okay, so Ka is equal to the concentration of H plus, concentration of C2H3O2 minus, over acetic acid. Okay, and that's going to be, let's go back to here, H plus is x times 0.050 molar over 0.100 molar, and that equals 1.8 times 10 to the negative 5, and that's the number we've got way back in example 3. Okay, so I need to work quickly. I'm kind of running out of time, so we can see that x is going to equal 3.6 times 10 to the negative 5. And notice that the x in this case, that is our H plus concentration. So once we know that value here, then we can say, well, what is the pH? Okay, so pH is negative log of 3.6 times 10 to the minus 5. And we've done that before. We know that the pH here is 4.44. I guess we haven't done that before. Okay, so that's our pH. If we know our pH, we know our pOH. So we've gone through and done our calculations, and we found out that the H plus was 3.6 times 10 to the minus 5. Therefore, the pH is the negative log of that, 4.44. Subtract from 14 to get the pOH, 9.56. We can use the pOH to calculate our OH minus concentration, 2.8 to 10 to the minus 10. And then we go back and we can do our percent dissociation, just taking x, okay, over the initial value times 100, and it's 0.036. Okay, the other two concentrations in here that were the acetic acid concentration and the acetate ion concentrations are essentially unchanged, but x is so small, and those are all our different values. That's examples 5, 6, and 7.